Good afternoon, everyone. Mm, Welcome to the fourth lesson of the Business Mathematics and Statistics. I hope you can recall what we have covered so far. We had an introduction session, that is lesson number one. And on lesson number two, it was very primitive session on the data presentation, merely on focusing on charts and graphs and a lot more on the presentation aspect of the statistics. And then last 2 weeks, students, we spent time on completion of the lesson on the numerical descriptive measures and central tendency indicators. So you could recall that we were having this problem of how to represent a particular data set by means of identifying one or two central tendency indicators like mode, median, and mean. There, of course, we discussed lengthy. What are the advantages, disadvantages, when to use what sort of limitations that these things are carrying, so on and so forth. And there, of course, students, we advance our lesson into more central tendency indicators such as variance and standard deviation. You all know that once we earmark something like mean, arithmetic mean, to be a statistical indicator for a data set, then of course afterwards we can identify, okay, how deviating or how variant from on average from one particular random data point from the mean that we could calculate for a particular data set. From that mindset, we went on to discussing on the advanced concepts of variance and standard deviation, such as covariance, uh, and then how to identify more than one variable coming into picture, x's and y's, and there, of course, the concepts of correlation coefficient and many more came into picture. So that I hope you can recall that now you are in a position to represent one particular indicator for a data set and give some sort of a statistical identification for a vast variety of a data set. It could be anything. Could be some counts of COVID positive cases in a particular country. It could be something like a batsman's score in T20 cricket. Could be the traffic for Columbus City, considering one of the A-grade roads in the country, maybe Candy to Colombo Road, maybe Gold to Colombo Road, likewise. Once you have this vast variety of raw data being collected, students, now by following lesson number 3, I believe you are in a position to give some sort of an identifier, representer for that data set, and tell, okay, on average there are 14,000 vehicles coming to Colombo, or else on average there are around 2,500 to 3,000 active positive cases in the country with respect to the COVID situation. Or for a batsman, his average is around 30 to 35. Likewise, once you express yourself with some kind of a number like that, then of course anyone could understand, okay, what's the average situation, what's the bottom line, what's the summary of the given picture. Rather, you present 1,700 cases one particular day, 3,000 cases one particular day, likewise. Or maybe for a batsman's case, maybe 0, maybe 100, maybe 50, and on some days 17, 18, likewise. If you just present these raw numbers, students, no one can get a perfect understanding. Just by giving one number and a standard deviation. And there are many more statistics like for instance, t-statistics. I mean, there are more advanced indicators and identifiers for these central tendency indicators per se, but we limited our discussion by considering the curriculum to give you the brief and the basic and the most essential indicators, and there we stopped our discussion. Okay. So today we are starting off a fresh lesson number 4. This is moving into 2 classes. There are 2 parts of our lesson. Because of the fact that one thing is the weight, and the second thing is that the discussion that we are going to start upon the next week, that is on the normal distribution, which will have some linkages to the lesson number 5, 6, and more. Now, you could recall that the word normal distribution that we are using has been already met before. Where is that? That is where when we were discussing things such as a distribution, whether you can see a positive trend, negative trend, no trend likewise, there you could understand, okay, for a single variable, for a single variable, if you put these values and their particular frequency, you can nicely come up with a normal distribution or a skewed distribution. Then the leptokurtic, mesokurtic kind of skewness could be also discussed, as well as some many more indicators could be discussed. So now we are going to start up our assumptions, thinking that more the data, thousands and millions of data being collected for a particular data set, students, we can assume that things will be falling into a normal distribution slowly. If you take maybe 30 or 300 or 3000 sample data, still your distribution could be a skewed one, or having some sort of a central tendency in different ways. But when you go for millions and billions of data points, students, eventually things are falling into so-called normal distribution. So all these mathematical sums that we're going to discuss under normal distribution will have this assumption, assuming that our data set is going to take a normal distribution. With that assumption only, we are going to do the sums and calculations. But that's a fair assumption as far as we can understand that ancient mathematicians and statisticians has proven that more the data and more the number of observations, your data set is going to take a normal distribution shape. So that is the latter part of our discussion on lesson 4. But the first part is we are going to take you through probability theory, give you a basic introduction on what is probability and what sort of equations and different combinations of probability that you can bring it in the normal day-to-day life. It's a very interesting student, I would say. Sorry, interesting lesson, I would say. Why? Because of the fact that probability, I've explained you this couple of times. In real world students, probability is something which anyone cannot really be escaped with. Some, I mean, if I just take you slightly away from the theories that we are discussing, sometimes, let's say you went out to go to work today. So I'm sorry, not today. Let's say tomorrow, Monday. Assuming that you're working in the office and not working from home, you're moving out from your home to the office. And on the way, you caught up with the rainy situation. And unfortunately, like in many cases, you have forgotten the umbrella. So what's the situation now? Now you're getting soaked with rainwater and things are getting messy. So if you knew that there is going to be rain tomorrow, likewise in many advanced countries, their weather forecasting system is way advanced than our system that we have in this country. Now assume you're living in Sri Lanka and you have to go through this situation. What really hits you? I would recall that it's a probability. I mean, nothing, one would say, okay, that's bad luck. One would say it's karma. One would say, okay, fine, there could be many other reasons that why I couldn't bring my umbrella. But all in all, you bringing in the umbrella is not the problem, but the rain is the problem. So what was the probability to rain on tomorrow? Could anyone name a number? Maybe 70%, maybe 30%, maybe 0%, maybe 100%. How to derive that number? That's all about probability theory, students. Now the probability theory is going to tell you that there are two extremes, certainty and perfect impossibility. In between these two numbers, 0% and 1%, 100% and 0%, there are numbers like 1%, 71%, 2%, 50%, 50-50 probability. So these numbers are going to tell you, fine, given any circumstance, given any instance, that your outcome, your favorable outcome that you're looking at, what's a favorable outcome for that first example that we discussed? That is not going to rain tomorrow. That will depend on the probability. That will depend on the probability. Could anyone name a number? What's the exact probability to rain tomorrow? And let's say if an advanced system going to predict you that there's a 52% chance to rain tomorrow, what would you do? Would you take your umbrella or not? That all depends on how accurate the calculation methodology. And what's your choice? At 52%, you may take the umbrella, or you may not take the umbrella. If you are a risk seeker, thinking that carrying an umbrella weighing maybe 400 to 500 grams in your uh, office bag is going to, take you through an additional weight, you may take the risk and walk out. But if you're a risk averse person, you will not take the risk and you will be scared of the probability that there's a 52% chance to rain tomorrow and you will still take the umbrella. So that's how you effectively make decisions from this. Now, still, I'm talking out of the curriculum. Still, even if you take a lot of jargon, which is coming from, let's say, medical to investments to economics, a lot of these theories are coming from probability itself. There are probabilities assigned to a lot of theories being calculated. So, for instance, even if you take a something like a rapid antigen test or a PCR test, how do you determine that there are these infected cells or these virus cells are being included in the sample collected? Still, it will be based on some sort of a probabilistic method. There will be a calculator, there will be a calculating mechanism, there will be a machine which will calculate its outcome based on some sort of a ones and zeros. If you have maybe 17 ones and 3 zeros, the machine will calculate, okay, 17 out of 20, that means I'm going to give you a red signal or a green signal. Likewise, uh, the machine will have to be calibrated based on the number that you're going to select. So, if you take something like an investment theory, still, how to invest in a particular company tomorrow, something like, let's say, 8 constraints. Are you to invest in tomorrow? How do you, without short selling, assuming that you are a long position holder, how do you really invest? You just think and you assume that the share price is going to go up. If the price of 8 constraints is maybe somewhere around 65 rupees tomorrow, why do you go and buy it thinking that there will be a dividend income and then there will be a price appreciation? How do you determine? Should you, choose this stock or, sorry, you have chosen this stock. Should you buy this tomorrow or day after, or should you wait for another month? How do you determine? All the theory will boil down to probabilistic estimates. Probabilistic estimates. So that introduction, I just want to highlight it before the lesson to show you how important this lesson is, and uh, to grasp these basic concepts that we are going to discuss under the IPSL curriculum. Try to get it in your heads. It will definitely be very much advantageous effectively when you are proceeding in your career. Okay, so with that long introduction, we will step on to the lesson on probability. Okay, so it's a numerical descriptive method how likely an event is going to occur. Now these are the important words to highlight. How likely an event is to occur. How likely it is going to rain tomorrow. How likely the 8 pence stock is going to go up by price tomorrow. That is my event. 8 pence price going up, raining tomorrow. Likewise, anything could be converted into a probabilistic event. So if at all you can assign some quantitative measures, then of course you can calculate the probability for this particular fact. Okay, moving on. Numerical measures of probability is a number between 0 and 1. See, 0 and 1. Where 0 is going to show you that there's impossibility, and 1 is going to tell you that there is a certainty of 100%. Now, the 0 and 1 could be noticed something like this also: 0% and 100%. 0% and 100%. 0 stands for impossibility and 1 stands for certainty. Could anyone assign probabilities like zeros and hundreds? Aren't there all the time? There's a random probability that there's 0.000 some percentage to occur something. Of course, it's up to the event calculator to define it. Sorry. So if the machine is way more advanced, it will not select something like zero. It will select something like 0.8 zeros and one. Still saying that there's not absolute impossibility, but there is a 1 in a million chance to happen something like that. Likewise, for the certainty also, students, there's absolutely depending on the say if your computer, calculator, machine, or the determiner is weak, then still one could say there's a 100% chance like this. But if you're using an advanced methodology compute, this 100% will be something like 99.9999 likewise. All right, that's some practical aspects. Third point. Probability of any outcome of random event is the proportion of times that selected event is being occurred over a series of repetitions. Higher the number of observation, greater the accuracy. All right. Now, look at point number 3. This is the important point. It says probability of any outcome of a random event is the proportion of times. Proportion of times that the selected event is being occurred over a series of repetitions. Now that share price going up, raining, all these things will have this same assumption. What is that? If you name your random event and you're going to call, okay, if that event is going to happen, I'm going to call it as a favorable event. Okay, so if at all, if it happens, I'm going to call it something like, let's say 1. I repeat the test. The next time also it happens. Another 1. Repeating the test. Third time happens. And the fourth time it did not happen. I'm going to denote it as 0. Fifth time it happened. Sixth time it did not happen. Likewise. Now, how many repetitions have I done this particular test to find whether my favorable outcome is being repeating? I've done it 6 times. And how many favorable outcomes? First, second, third, and fourth. And if at all, correct. If at all, now one asks me, okay, what's the probability that this is going to happen? Following my tests, I'm going to tell you it's going to be 6 out of 4. Now those other probabilities that we discuss in the real world, can one do the same thing? Of course. Training this Monday would be a day in a week. One would take 52 Mondays in a year. One would take Mondays of every first week or second week likewise. One would take any days, 365 days, and we'll calculate, okay, what's the probability of raining tomorrow in Colombo? Likewise. And there will be some favorable outcomes, some not favorable outcomes. Likewise, once you calculate all these favorable outcomes and divide it by the total number of repetitions in your test, now that is how you calculate the probability. That's why at the beginning I told you, how are you going to assign a probability? Now this is the only way to assign a probability. You have to repeat that test again and again and find some sort of a favorable and unfavorable situations. Take the favorable outcomes, divide it by the total outcomes. There only you can calculate a probability. If you take 8 constraints stock example, could be the same thing. Over a day, I'm assuming that whether my price is going to go up or otherwise. So you take day 1, price went up. Day 2 went up. 3 down. 4 down. 5 down. On the 6th day, again went up. So likewise, you take this number of repetitions as far as you like, as far as you can calculate, and then you can calculate the number of favorable events. So that's how you simply calculate probability. Look at the last point. That's also very important. Higher the number of observations, greater the accuracy. Now, if you take 8 constraint stock example, I would say, okay, first day it went up, fine, happy. Second day also it went up, happy. Now, if you stop your tests over there, what's the answer? 2 divided by 2 It's 100%. 2 divided by 2, 100%. Now, lesser the number of observations, there is a danger entailed. But what if you go to the third day? I told you 2 days stock went up, third day down. Now, third day it went down. Now, what's your total outcome if I just write it while discussing? First day went up, up, down, 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 and then again up and up. If you stop your discussion over here, what's going to happen? Your probability is going to be something like 2 divided by 2. But what if you move to here? Now situation is getting interesting. 2 divided by 3. 3 instances, first, second, and third. Fourth, more interesting. 2 divided by 4. O equal to 1 divided by 2. 50, 50. Now consider this point and this point, students. See how vast the number of observations can make. So that's why eventually, I think at the very couple of lessons ago, we discussed that misrepresentation of statistics part, if you could recall. Now this is a classic example. You should not depend on a smaller number of observations. Always, if permits, you should go for the maximum number of observations in order to get a better result, better probability. Okay? Right. So in probability, now these are few definitions, or rather I would say few naming conventions. An event can be a specific outcome or a set of outcomes. What do you mean by that? Event could be something like, you take a dice. Now in probability, students, there are some 3 or 4 things which are very widely used. What are those? The first thing is something like a fair coin, which will have the heads, and the other side, this will have something called the tails. Then there is a 6-a-side dice, D-I-C, dice. Something like 1, 2, 3, and on the other sides, there will be 4, 5s, and 6. Then maybe 52 card deck. Something like 52 cards are there, and then there are clubs, aces, and hearts likewise. So you can make different choices. How many kings, how many queens, how many colors, likewise there are few more examples. Now why do we really discuss about this? These are things that you can really start discussing the probability and try to understand the probabilistic theory very easily. Why? Because once you toss a dice, once you toss a coin, can anyone tell you what's going to happen, whether it's a head or a tail? I mean, why is it in a cricket match when when you're going to select who is going to bat first, or ball first, or I mean, one of the captains will have the choice to select that. Why do you toss a coin? That's simply because of the fact that we assume that by tossing a coin, no one can tell exactly whether, unless it's for a biased coin, no one can tell whether it's going to be heads or tails for a particular one toss. But if you do twice, still you can't tell. But if you do it 3 times, 4 times, how many times, no matter how many times you do it, your outcome is going to be random. So we call it as something like a random event. So an event could be a specific outcome, something like getting heads or a number 6 of a particular coin or a dice, or a set of outcomes. What do you mean by a set of outcomes? In a dice example, you getting an odd number or an even number. Likewise, there could be more than one. 1, 3, and 5 could be one particular set, and 2, 4, and 6 could be another particular set. So it could be one outcome or a set of outcomes happening in probabilistic terms. So that's the very first definition. Second definition, sample space. near the avakasha, sample space. This is the list of all possible outcomes for a given test. So something like for a dice example, it could be heads, it could be tails. Oh, we call it another set. This thing is there. That is a null. What do you mean by null? Due to some random event, none of this could occur also. Absolutely random event. So theoretically, students, once you are defining the sample space, we'll be discussing in a little while. Once you define this sample space, it's always should be practical to keep one particular space for the null set or the empty set also. Or we will be discussing. So the sample space for a dice example could be 1, 2, 3, 4, and 5, and 6. Heads and tails could be simple terms. Heads and tails could be the sample space for a coin example. For a 52 card deck, 52 all these individual events could be the sample space. But what if you define things in a different way? What if you define your sample space in something like odd numbers in a dice? So it won't be 1, 2, 3, 4, 5, and 6 anymore. It could be 1s and 3s and 5s and likewise. So the sample space, don't really get confused. It does not comprise of the individual events. Rather, it could be the individual events if you don't define it in a specific way. But if at all you define things if you define your events in a different way, your sample space is going to carry out different elements. How do you typically denote a sample space? Is by this, something like this, small two brackets, something like heads and tails. It's a simple example. 1, 2, 3, likewise 5 and 6. Then you close these brackets. So typically in probability, students, once you have these small brackets like this, we can denote it as a sample space. So whatever which is written in here is denoted as the sample space. Third, the randomness. If events or outcomes occurred are equally like to occur, it is called the randomness. That's why I told you at the very first example, once you are discussing about this coin flipping for a cricket match, we assume that both heads and tails are going to have some, random probability, the same random probability to occur. What do you mean by this randomness? That is the idea of that all individual events are going to have the same probability to occur. What do you mean by a biased coin or a biased dice? You slowly shift the weight of this coin or the dice to one particular end. Something like you carve a little bit, or something like you add some more weight to one side. Then what is going to happen? Once you're flipping or once you're tossing or throwing away, due to the aerodynamics, once you toss it over some empty space, then the probability is not going to be 50-50 anymore. Something like 60-40. Bias probability. So in such events, we can't call it as a random event. It's not a random event. If it is purely random, then coin flipping has to be 50%, 50%. Dice throwing should be 1 divided by 6, 1 divided by 6, 1 divided by 6, likewise. Okay. Fourth element, complementary event. Now we discussed about the so-called word event, and now we are going to discuss something called a complementary event. The complementary event is nothing but the probability that selected event will not occur. We call it as a dash. Dash. What do you mean by the dash? Dash is going to tell you something like A is my event. A dash is going to tell you that this is the complementary event. For instance, if A is the raining, A dash is not raining. Simple as that. So, lastly, if I define the event and the complementary event, then I can come to this easy and very useful theory of adding up the event and the complementary event, what is going to be. So if at all, let's say this A is going to be my rain example. So now let's say there are some clouds over here today, and there's going to be some sort of dry winds going here and there. So I can see some less rain, less light being poured to the earth. So that all gives me a sign of rain. So I'm going to assign 70% as the event that I'm going to call as the rain tomorrow as 70%. I didn't repeat this test, but randomly I put this number. Okay. If this is 70% students, what is the complementary variance probability going to be? It is going to be 30%. Why is that? Simply because of the fact that I have defined these events in a way, okay, what is the probability of raining tomorrow? 70%. If it rains tomorrow, okay, fine. There is a 7 divided by 10 number of chances that there is going to be rain. So what about the other three? That other three is going to be my complementary event. That other three is going to be my complementary event. So eventually what is going to happen? If I add add these two together, this is going to give me 100%. So that's why we can call it as for a given event plus that given event's complement. This is the given event. This is the given event's complement. The summing up is going to give you 100% or 1. It's one of the simplest probability theories. Okay. Few theoretical areas: empirical probabilities and classical probabilities. So the basic idea, the broad idea is that the empirical probabilities are going to calculate based on the actual data, while classical probabilities, these are also called the theoretical probabilities. These are calculated with the assumptions that based on some formulae, based on some principle, based on some beliefs and theories. So the broad idea is that if at all, let's say this coin flipping example, if you do the actual experiment, see this example, flipping a coin 100 times and you're getting 56 times the head. Now you're going to call it as probability of heads is going to be 56%. If you derive into this number by following this test, you can call it as a empirical probability. But if you don't have the time to do this test, then even if you say fine, I don't really need to do this test, and then go for the testing straightforward. I mean, if you take the cricketers example, do you think that before going into the pitch, the umpires or the captains, they flip this coin maybe 100 times and test whether they are getting exactly 50 heads and tails, and then only they go for the test? No, not really. They just take a random unbiased coin, and then the umpire will hand it over to the captain to maybe the flip in, and then everyone knows that there's a 50-50 chance, and depending on the heads or tails, everyone will accept the result without challenging. Such probabilities are called the classical probabilities. For instance, an unbiased coin is flipped. We can call the probability of heads is going to happen as 50%. Those are the broader two branches of probabilistic estimates. Empirical probabilities, you do the testing. Classical probability, you go ahead with an assumption. Okay. Fine. Now we are coming into the computational parts. If a six-sided dice is tossed, what is the probability that it will land with the value 2 on the upside? See, now we can define our sample space. It's going to be 1, 2, 3, 4, 5, and 6. What's the event of interest? That is 2 is going to stay on the upside. So if that is the case, we can call the probability 2 is going to be 1 divided by 6. How many times? 1 time out of 6 times. So simply, students, this is how you are going to calculate the probability of an event, number of positive outcomes or favorable outcomes, or the outcome that you're looking at, divided by the number of total outcomes. That's the broader and the basic concept of probability. That's how you calculate the probability, which we discussed already. So bringing in some more, how do you call it, the notations. This simple part, I really want to focus. Px, this P stands for the probability. P stands for the probability. Once you put up a small bracket like this, now this is your favorable event. This is your favorable event. So something like probability rain. Then you can call it a number, something like 70%. That's it. Okay. So you can write this Px. X is typically we put it as a random number so that anything could be replaced by x, is in between 1 and 0. What are these signs? Greater than or less than. But why did I put this equal specifically? Simply because of the fact that we discussed at the beginning, there could be impossibility and certainty instances also. So 0 is where no chance of probability x is occurring. And 1 is where 100% certainty probability is going to occur. And something like 0.1% or 1 divided by 10 or 10%, that is a classic number of the probability for this particular Px. A good example, there is a 40% chance that there will be a depression of world economy by year 2021. 40% chance, that's the probability. So what's the event? That there will be a depression of the world economy. This is the event. So what's the complementary event? There will not be a depression in the world economy. What's the probability of that complementary event? If this is 40%, that is going to be 60%. Okay. All right. Few examples for you to try on your own. A coin is flipped 200 times. It landed on its head 105 times. What is the probability that it lands on the tail? Shall we do this exercise? I want you to try. We have sufficient time today. Coin is flipped 200 times. It landed on its head 105 times. What is the probability that it lands on its tails? Difficult question. It's very, very easy. Okay. What's the answer? If it lands on its head 105 times, what happens to these other 95 times? That's the number of times that it is going to land on its tail. So this is going to be 95 divided by 200. This is the answer. 95 divided by 200. If you take it in a bit more different aspects, something like 0.475 is also a good answer. Something like 47.5% is also a good answer. So any of these methodologies will be accepted as the final answer. It could be a fraction. It could be a decimal number. It could be a percentage. Could be anything. Same number. Okay. Second question. Two unbiased dices are rolled at the same time. Two unbiased dices are rolled at the same times. What is the probability of getting number 2 and 6? It's a very good question if you could try. Two unbiased dices are rolled at the same time. To assist you a little bit, let me do a bit of a drawing here quickly. Two 2, not one dice throwing multiple times, but one time, two dices. What is the probability of getting number 2 and 6? These probability questions, students, different people can argue in different instances, but there will be, depending on the English, depending on the wording, depending on the examiner's point of view, there will be only one correct way of thinking. For this question also, you can argue with me on different angles, but let's see whether we can come up into the same argument. What's the probability of getting number 2 and number 6? What is the probability of, now second question, what is the probability of getting 2 ones and 2 sixes? Or third one, what is the probability of the sum of the two dices less than or equal to 5? These are very good questions to think. Okay, to make things interesting, let me try something like this. Okay, if I take the first dice, what are my outcomes is going to be something like simply, okay, 1, 2, 3, 4, 5 and 6. Okay. What about my second dice? Now, if I get number 1 over here, what about my second dice? For that dice also, I could get something like, again, 1, 2, 3, likewise. Isn't that so? So students, to make things very interesting, I think I can come up with something like this. If I take the first dice, 1, and I'm going to stop it there. And the second dice is going to get something like this. 2, 3, 4, 5 and 6. Now this is the first dice and all the other are the second dices. See, the first dice, I'm going to lock it here. I'm going to lock it with 1. Okay. Fine. Now you can think something like this. Okay, if this is the case, if I lock the first dice again to number 2, similarly, there will be numbers like to here. 3. Again, numbers like here. 4, 5 and 6. Now this is the complete picture. Sorry. If I quickly, mark all these spaces with ones, dashes, so we can make it very comfortable at the end. Why? Because of the fact that we have to not really take one particular instance, but rather see how many total different combinations that we can bring it in this simple question. What is the probability of getting number 2 and number 6 are? Now, I'm assuming, okay, this is my way of arguing. I'm assuming now, the examiner is thinking of one dice getting number 2 and the other dice getting number 6. One dice getting number 2 and the other dice getting number 6. Okay, let me quickly erase these things and reword it so that the other questions, it will be a bit easy for us to discuss. 1 and 1. Okay, now how many instances now you can find here, students? If I take something like this, the first one, 1 and 1, is it a favorable event? No, not happy. Second one, no, likewise. So if you take the first the whole row, no outcomes. But what about here? Now here you have one of these favorable outcomes. Why? One dice is going to give me number 6 and the other dice is going to give me number 2. Fine, I found one happy instance. what does the question says? It says, what's the probability of getting number 2 and number 6? So one has to be something like number 2 here, and the other has to give you something like number 6 over here. So this is one such instance. Okay. What if I take number 3 row? Not happy. Why? All one instance is be locked by number 3. 4, same case. 5, same case. But about 6, here also I can find another instance. Now this is all I could find. If at all anyone could find any more combinations of 2s and 6, we might guess and spell it out. So otherwise we can comfortably finish this argument and calculate the probability as 2 divided by how many events now here? 36. 6 to this side and 6 to that side. Okay. So this is the answer. 2 divided by 36. 1 divided by 18. This is the probability of getting 2 and 6. See the wording is very simple, but how many steps that you have to go through to do a calculation like this. Now, since I did the hard part, could you try number 2? What's the probability of getting 2 1s and 2 6s? 2 1s and 2 6s. It's very easy now, isn't that so? Why? Now, if I do the drafting over here, there's another 6 and 6 here. 2 1s and 2 6s. That means either 1 1 and 6 6. Again, the same probability, isn't that so? 2 divided by 36. Hope you are following. The answer is going to be these two events. 2 divided by 36. Third one, what's the probability that sum of the two dices, I have put it in a bracket also, sorry, chords. Sum of the two dices is less than or equal to 5. Now this is going to be interesting. The sum of the two dices are going to be less than or equal to 5. What does that mean? Now if you take something like this one, let me erase these drawings for the last part. Okay, if you take something like 6, this is 6 and 6, this is 2 and 2. Okay, sorry, this is 6 and 2. If you take something like this particular part, 1 and 1. Once you do the summing up, students, what's the sum? 1 plus 1 is 2. This is 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. And 1 plus 5 is 6. Now, this instance is going to be not taken into consideration. Why? The sum of the two dices is going to be less than or equal to 5. So, if at all you see an instance up to here, you can take it. But the other ones are giving you the sum more than this. 2 1, good. 2 2, good. 2 3, fine. 2 4, taken out. 3 1, 4, okay. 3 2, okay, fine. 3 3 is not taken into. Is that it? No, there's one hidden here also, see. 4 1 can be taken. All the other ones, 5 1, 6 1s, now these ones are going to have the sum more than 5. Sum more than 5. What's the answer? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divided by 36 is the answer. Sorry. 10 over 36. What do you think? Probability questions are difficult. It could be difficult if at all you cannot focus on how to decompose, how to simplify your situation. Look at the third question. There are 3 black pebbles and 3 white pebbles in a bag. 3 black pebbles and 3 white pebbles in a bag. Now, to make things interesting, students, I would strongly recommend whenever you're trying a probability question, always stick to a small diagram. This is the bag. 3 black pebbles, B, B, and B for black. And okay, my bag space, I'm going to expand it a little bit. And I'm going to use a different color. White, white, and white. Now you don't have to be shy. I mean, as in for a simplification, always stick to a diagram. Because if at all you don't do it, there is the graphical representation always going to make things easy. Even for me, sometimes things could go wrong if I don't get the scenario thoroughly to the head. There are 3 black pebbles and 3 white pebbles in the bag. What is the probability of getting a white pebble if we take 1 pebble out? If you randomly put your hand into this bag and you're not looking at the color, just pick 1 pebble. What's the probability that it is going to be white? Simple. 3 divided by 6. Why? There are 3 white pebbles, 3 black pebbles. So what's the, if you take 1 out, it's going to be 1 divided by 6, 1 divided by 6, and 1 divided by 6 for the, these are for the black guys. And for the white guys, 1, 1, and 1. So this is going to be the total. These 3 elements together is going to calculate my probability as 3 divided by 6. Okay, hope that is clear. Given the first pebble above is black, now what is the probability of getting a white pebble? Okay, what do you think? Given the, focus on the question, given the first pebble above as in this first tester is black. Now what is the probability of getting a white pebble? I would like to see an answer here. Now we did the complicated math, and I really want one of you to try and think a little bit and give an answer. Don't worry, your answer doesn't have to be perfect. We are learning. So, okay, Shahan, any more? Excuse me. Good. I think we all are getting it there. Great. Now, how do you argue in an instance like this? Simple. You take 1 out. How many pebbles are there now? 5. Now, what is the probability of getting a white pebble? White pebbles are intact. They're not being taken out. So, there are 3 white pebbles. Simple as that. Think a lot of you are getting there. Good. So students, all about this probability game is depending on how you define your scenario and how one can argue. I mean, for a question like this, dices and these pebbles, one could argue in a different instance also. So always be careful with your argument. And never forget the fact that for your examination, there is one examiner, and that examiner should be thinking the way that you are thinking. So don't be very creative, but rather think rationally. Think rationally. Instances when there are no data being given. Now in this black pebble, white pebble example, I've not given you whether these pebbles are equal weight, whether they're same size. I just given you the color. Given you the color. So one would say if the black pebbles are, let's say, slightly smaller and the white pebbles are slightly bigger, in such case, one could argue thinking, okay, there are not enough data given, so we can't really make a judgment, because once you put your hand blindly into the bag, still, okay, depending on the size of the pebble, one could think, okay, be creative. One could think, okay, the test is not going to be random, but don't be like that. Assuming, now whenever there are data not being categorically or specifically mentioned, you have to be assuming those facts. It's always good to mention your doubt or mention your assumption, thinking the pebbles are same size, thinking the pebbles are the same weight, physical size. put it in an assumption and then conclude your answer. Okay, so I really want to tell you that when you're doing the calculation, the only tricky part is depending on your mindset and the question's mindset. Okay, moving on. Now, the probability theory could be easily and very graphically represented by this set theory, set, Kulaka, set. This set, the broad idea is that you demarcate. Now, in the sampling examples, you could recall, you have this bigger box, we call it as the population, and then the smaller area, we call it as a sample. Likewise, the set theory exactly use that same notation, same principle. It's nothing but a graphical representation. It doesn't really have to be sticking to a box and a small squares or circles. It could be anything. It could be a freehand drawing. Don't worry. But the broad idea is that it is going to identify whatever the events and the outcomes into groups and bundle them together. You're going to bundle them together. And then you can identify whether you can see crossing instances, mixing instances, common instances. Likewise, you can easily identify. And what's the last outcome? You can come up with theories. There are things called the set theories, and we are going to conclude our lesson today with some probabilistic theories. The set is the easiest way to identify how these theories are going to commit into the place. Okay. A set could be simply defined as a clearly identifiable group of items bundled together. Told you, similar items, we are bundling it together. Items that could include in the set could be identified as its members or elements or events. Anything could be included in a set. Okay. So usually one element is not replaced in a set, while a comma could be used to separate elements inside a set. Okay. So likewise in our sample space, we can use the same simple brackets to classify a set. See? So one example to denote a set could be using simple English. Something like this. Even numbers between zeros and tens. Once you do the classification, your outcome is going to be something like 2, 4, 6, and 8. Assuming that 10 is not being taken into place. And you can denote it again by using the so-called Venn diagram. VENN, Venn diagram. Venn diagram. This is a Venn diagram. This is a Venn diagram. This diagram is going to show all possible logical relationship between a finite collection of different sets. That means for a different number of elements crossing and intersecting together, you can denote it in a Venn diagram. You can denote it in a Venn diagram. So the simplest way to explain the Venn diagram is by taking only two such sets. This is the set A. This is the set A. This is the set B. Okay. What do you mean by this sign epsilon? We have made this sign before. Epsilon. This is the total set. Total set as in once you put up something like an epsilon here and then once you draw the demarcation, it gives you the idea, okay, fine, this whatever the outcomes that I'm going to discuss is inside this particular range. Inside this particular range. Okay. So if I highlight something like this, sorry, I have a highlighter. If I highlight an area like this, this is the area that belongs to set A. And if I take another highlighter and highlight an area like this. This is the area which belongs to set B. And what about this area? This particular area. This is the area which is common to set A and set B. Common to set A and set B. Is that it? Is that all that we can define? Don't forget the fact that there's a huge, vast area which we did not demarcate so far. Sorry, my highlighter is moving a little away from the epsilon set or the total set. So I want to briefly overview and tell you, okay, yellow set A, green set B, and the orange other items other than set A and set B. And what about this beautiful area that got crossed away? This is the items that are common to A and B. A and B. Okay. Simple example. In our early days of maths, this is how we denote. A could be number of, let me do a fresh drawing. A could be number of households with televisions. B could be number of households with radios. What's this? Something like, so let's say I'm going to put up some numbers here. Televisions, I'm going to denote it as something like 40. I've done a test in a particular village and I found 40 houses are having televisions. And more than that, actually, 70 houses having televisions and radios. Sorry, radios only, yeah, radios only. And then this particular part I have found, okay, in 20 houses, I could see both televisions and radios. Both televisions and radios. And the total number of households that I have done this test is 200. Now I can bring up the other areas. If I have 40 houses with televisions and 20 houses with both televisions and radios, that means there has to be 20 houses only with televisions. Yeah. If I have 70 houses with radios and 20 houses with both radios and televisions, that means now this space is going to be something like 50. 50 houses with only radios. Easy as that. 40 televisions, 70 radios, 20 both televisions and radios. What about this space? Can anyone think? What about this space? How many? What's the number and how do you define that number? How do you calculate it? How do you calculate it? Simply by taking the addition. 40 here, greater, yeah. So I have 20 here, 20 here, that means 40, 50 here, 90. So this is going to be 110. Is my math correct? 110 plus 20 plus 20 is 150 and this is 50. So my epsilon or the number of total households that have done this test is 200. That means there are 110 houses without a television and without a radio set. Okay, so this is the simplest way of calculating the numbers or the areas by using a Venn diagram. So Venn diagram, students, is going to easily demarcate the areas. Now let's bring in the symbols that is used in the probabilistic theory. There are two symbols that we commonly use. Now we have been introduced to this dash previously. Dash supposed to be something like the complementary events or the opposite of the event happening. The reciprocal, other side, flip side. Other than this, now we are going to introduce you to two different symbols. We call this as the union and intersection. union and sorry union and intersection. Sorry. What are these two symbols? We use symbol U to denote this mark called the union, and this U on the other side, flip side, 180 side to 180 degree side to demarcate the intersection. Now, why do we do this? Is simply because of the fact that now we are going to discuss the combinations that we can think from the point of view of these Venn diagrams into probabilistic theory, into probabilistic theories. Now, one can say, okay, probability of televisions and how radios. Likewise, one can write. But of course, students, once you are going to, trying to demarcate the advanced theoretical areas, it's always easy to use some sort of mathematical demarcations. That is why this union and intersection is going to be very handy. Union is simply going to tell you nothing but the addition. Union is nothing but the addition. The broad idea of the union, P A union B, is going to tell you, okay, give me the probability that P A and B, A and B. That means basically this whole idea. Although I use the word and, A and B and, this and sign actually in probability language demarcates not for this union but for the intersection. But the English idea is that the P A union B is finding an event that is going to stay in either of A or B. Could be coming from any of these areas. P A union B, this whole area. Forget about this calculation for a moment. Forget about this part for a moment. Where do we use the intersection? Where do we use the intersection? Sorry. The intersection is trying to identify, okay, what is the commonality between these two sets? This particular area, intersection. PE intersection B. That means in probabilistic English, we can call this PA and B. PA and B and PAOB for the intersection and the union. Intersection and the union. Okay. Now this is something I'm going to discuss at straight, but try to understand since it's nothing but purely argument from the diagram's point of view. The first equation that I've written here, PA union B, I have demarcated like this. Now these probabilities, the addition of these probability students is going to be very easily understood by the Venn diagrams or the color diagrams. I have highlighted it here. This orange color highlighted area is the answer for the PA union B. So this is the PA union B area is what is highlighted here. Okay. Now, for one to calculate this, you can add these probabilities separately. Okay. If I take the PA, what is the PA? This, sorry, different color pen. This PA is going to come from this particular area. Okay. For the PAOB or A union B, now I have taken the first part. This is done. Now I'm going to add the second part. What is that? PB. Okay, now I'm going to add it again. fine, okay. This area is fine, covered, okay, fine. Now once I'm going to cross here, what about this dotted area? Once I have done this, students, what I have done here is that I have double counted this area, isn't that so? Why? This is already added to my equation in probability A. This area is added. Once I'm adding the probability B also to the probability A, I am double counting this shaded area. What is this shaded area? We have already discussed. That is the P A intersection B. That is nothing but P A intersection B. Now that is why I am deducting it once. That means, students, effectively, I am taking out this double counting problem. Isn't that so? Now this double counting problem is taken away. Why? I have deducted it once over here. Deducted it once. So effectively, PA union B can be calculated as PA plus PB minus PA intersection B. This is how you can graphically explain it using the Venn diagram. Or another instance is that we remember, okay, any event can be discussed with the complementary event also, isn't that? It's a complementary event. So if you take this A union B dash, what is that area? This is that area. This is another way of explaining the A union B. What I have done here, I have taken, this is the P epsilon, and this is P A, what is the area that I highlighted already? This is the P A union B's complement, or A union B dash. Be careful, this dash is after the bracket, not A union B dash. Don't be misjudged by it, sorry. So either I can write PA union B is equal to PA B minus PA intersection B, or again PA union B could be easily demarcated by using it complementary event. So you take the epsilon and then take out the complementary event. So that way also I'm going to stick with the P A union B. So why did we discuss all of a sudden with the Venn diagrams and this union and intersection? Now this is the starting point of all the complex mathematical relationship between a two set theory by the introduction of the union and intersection. There's no easy way to simplify this, rather to use your own imagination and identify what is union and what is intersection. Union, probabilistic English, we can call it as O. Intersection and union O. Now let's see some explanations. This we already discussed. What is this? P A intersection B. That is the part which is highlighted here. Or the commonality. How many households with radios and televisions? PA union B complement. This is what we used previously. This whole area. A union B is the highlighted area. Once you are discussing about its complementary event, what is that? That is the whole area minus the A union B. It's a very interesting concept. What is PA? PA could be taken like this also. PA minus PA's complement. PA's complement. PA's complement. So this is PA's complement, this whole area. If you take probability epsilon, what is that? This is going to be 1. This is probability of epsilon. Yeah. So that way also you can define probability A. Now I'm bringing in this probability of B minus A explanation. B minus A. What do you mean by the B minus A? Is the idea, okay, What's the area which is only unique to B? B minus A is the way to write it in probabilistic language. What's the area which is only unique to B? If I take PB, I have to calculate this area also. I calculate that area also. But it is not the case that I'm looking at. Not probably B, but only to B. Only to B. B minus A can be calculated simply like this. You take the A complement. You take the A complement. Okay. What's the A complement? This particular area that I'm putting the dots. This is the A complement. And I'm finding the commonality and B. What is B? Let me use a different color, green color. Sorry, green is not very visible to you. If I use the red color, that's better. This is B. Now don't forget the fact that I have to go to this area also. Why? This is B. Ah. So where are the common events? Where you can see the both both these dots. That means blues and reds. Is it going to this area? No, it's not going to over there. So A complement A dash intersection B is going to easily give me the B minus A calculation. B minus A. This is not the only way. Don't be scared. This is not the only way. You can take more things like epsilon and 1 and find B minus A also. But this is one of the easiest way to define B minus A. Okay. So these are few different things that you can define using a Venn diagram. All right. Fine. Moving on with the Venn diagrams. We can denote probability X to define probabilities by utilizing the data of a Venn diagram. What do you mean by that? Px stands for calculating the probability of any random event. That means we can calculate the probability of any random event by using the data, by utilizing the data of a Venn diagram. I mean, inevitably, that's what we did in this very previous television radio case. Since we are a bit familiar with the numbers now, try to calculate these values. PA, PB, PANB, PAOB, and PAOB dash. Let's try to get some numbers here. What's the probability of A? PA. Any answers? Excuse me. Difficult? Easy. First, we have to find the epsilon value, or the total number of events, total number of occurrences, total number of households. What's that number? How do you calculate it? Simply try to, assume and calculate the area. This area is 15. 15. Okay. This area is 12. Counted. This area is 8. 12 plus 8, 20. 20 plus 15 is 35. And what about these all other areas that we did not cover? It's 15. That means, students, the epsilon is 50, isn't that so? Am I getting it correct, or epsilon is 50? Total number of households, events, items are 50. 15, 15, 30, 30 plus 20, 50. If that is the case, PA is going to be Nothing but 15 plus 8 is the area for A divided by 50. 23 divided by 50 is PA. PB, easy now. 20 divided by 50. PA and B. A and B. A and B means this particular area. 8 divided by 50. See, once you define your areas, it's very easy to calculate any probability. PAOB, easy. Either I can add up these things or I can take 50 minus 50. 35 divided by 50. If I add it up also, 20 here, 15 here, 35. PAOB complement, this value, 50. 15 divided by 50. See, so it's all about defining your area separately. If at all you don't know the value of one particular area, then you are in trouble. Still, you have to get it calculated. Something like do up a Venn diagram like this. What do you think now? There are many more calculations. This is television. This is radio. This is, let's say, bicycle. What is this? Households with television, radio, and a bicycle. What is this particular area? Something like this one. Households who are having radios and bicycle. Something like this particular area. Households having televisions and bicycles, but some may have radios also. That's how you define things. So the wording has to be very careful. Wording has to be very precise to calculate something like this. So you may given 5 here, 6 here, 7 here, 10 here, likewise. Then if this is the case, you have to find these missing pieces first. Then only you can use a Venn diagram to do a computational probability like this. Okay. Are there any questions so far to resolve? No, great. Okay. All right. Now, so far we have discussed few interesting areas on probability, Venn diagrams, areas, and we have defined few more theoretical probabilities like the addition of one and its complementary events, the summations. Now, this is where under this rules of probability, we are bringing everything into few acceptable rules. Okay, so bear with me. Some of these things we have already discussed, but this is how we are formally putting it into rules of probability. Why do you need the rules of probability? Simply because of the fact that given any circumstance for a random event, for an event with assumptions, how to calculate probabilities of your favorable event or any other events that you want. Okay, fine. The first rule, range of probability. We have discussed this already. This is how you denote it officially. Probability of X is always between 0 and 1. It is not 2, not negative, no, 0 and 1. Okay. The summation of probabilities. Probabilities of all outcomes in a sample space must have the sum of 1 or 100%. This is how we're going to put it. Sigma I equals 1 to n. This sigma, we have met it already in our statistical career. This means, for this to be perfect, this has to be sigma I equals 1 to n p x I. Sorry students, this I is missing here. Why do I need the I? This means, okay, this is adding up p x1, plus px2 plus px3, likewise up until px simple n. This is the addition of all these individual probabilities. Addition of all these individual probabilities. Once you add up all these probabilities, students, this is something like, let's say, 20%, this is something like 5%, there's another 10% probability for this one, 15% probability for this one. Likewise, students, once you add up all these individual probabilities, what is going to happen? This is going to be total 100%. It cannot exceed 100 or it cannot exceed 1. So we officially put it in a rule saying that the summation of all the probabilities has to be 1. That's the second rule. Third one, complementary event. Probability of an event plus that event's complement is also 1. That's how you put it. Px plus px dash or e in this case is going to be equal to 1. That rule, we have met it already. Now these are the rules that is going to be a bit new to you, and we're going to learn few new things over here. Let me quickly forward up a little bit up until, yeah, okay. We're going to discuss up until rule number 6 and move on to the past paper questions today. Okay. First, conditional probability. We're going to spend some time here. The idea of conditional probability is that there are more than one events that is going to discuss in the conditional probability jargon, and then that particular event is going to have a dependency for the second event to be discussed. That event is going to have some sort of a dependency for the second event to be discussed here. The first case is that the notation. Notation is going to be something like this. Something like this. There is this straight line, this dash, this one. That is the sign that is going to denote fine. We are talking about a conditional probability. We are talking about a conditional probability. You can't be creative and put something like this. P A. No, this is A divided by B. Don't get misjudged by it. Be careful. Your line has to be a straight line. P A given B. Given B. It's a vertical straight line. Okay, that's the notation. So what about this A and B? Sorry, again, one more thing which I missed to mention. This is the notation, and this is how we are going to call it. A given B. A given B. So effectively, this is A, this is the wording for given, and this is B. A given B. Okay? Fine. Now let's try to define the conditional probability first. The conditional probability is the probability that a dependent event will occur. That the dependent event will occur given that another event has been occurred. Given that another event has been occurred. Now let's try to quickly jump into here. That's why I need to define the wording first. What about this particular part? I have demarcated as probability A given B. A given B. Now read the area again. Dependent event will occur given that another event has occurred. A given B. That means this A is going to be my dependent event, or the event that I'm focusing, or the event that I am trying to calculate the probability. What about the B? That is the event that has already occurred. That's the event that has already occurred. That's why we demarcate as A given B. A given B, and this is how we write it. So something like Probability A is I am taking the umbrella in my bag. It could be something like 50-50. One day I may take it, one day I may forget it. B is it's going to rain tomorrow. It's going to rain tomorrow. So probability of A given B in that case, how do you demarcate it? Probability of A, that means probability, what's the probability of I am having the umbrella in my bag given it has rained, or given it is going to rain tomorrow, or given it has rained. Any tense is fine. The broad idea is that, students, now if you know the probability, these two probabilities individually, independently, you can calculate the probability of these two events together. That is why the conditional probability has a separate theoretical area for these computations. Now, how do we calculate this? How do we calculate this? Is simply by, again, by taking the uh, deviation between the A union B, sorry, A intersection B and PB. A intersection B and PB. Now, examples like this umbrella and raining could be a bit more difficult to think on this jargon, but shall we try to think it on based on something like a Venn diagram. Venn diagram. PA given B. So this is going to be something like you have A, B, this is the commonality. What I have highlighted here is P A intersection B divided by PB. This is the area of P A intersection B, and this is the area of PB. Once I divide these two, let's say I have commonality of something like 10, probability of B is something like 50, and then simply my PA given B can be replaced by these numbers, 10 divided by 50, 20%. Yeah. And also, interestingly, students, now this A and B, since these are items, since these are events on their own, we can even replace them also. If you try to simply think on perspective of my umbrella and rain example, I earlier wanted to argue from the point of view that what's the probability of I am having the umbrella in my bag, provided that it is going to rain tomorrow. On the other side, if I try to argue, I can tell something like this. What's the probability of it's going to rain tomorrow, provided that I have umbrella in my bag? So these two events are going to give you two different probability numbers. Don't forget the fact that it's not going to be the same number, two different numbers. If I write the wording again, simply try to get the same idea. Use the same Venn diagram, A and B. Now in here, is it A given B or B given A? Now this is B given A. Now, this part is common, fine. P A intersection B, that's fine. But now this is the PA, the PA. So P A intersection B part is fine, divided by PA is going to be my probabilistic case in that case. Yeah, it's a different number. So broadly, students, conditional probability is going to tell you on combining two different instances, but not we are multiplying it. I mean, there are different areas of theories in probability, like independent events and mutually exclusive events for that. But merely given the event has occurred, what's the probability of my second event, or the dependent event, or the event that I'm looking at is going to occur. That's a broad idea in conditional probability. Yeah. Last point, inverse. Conditional probability of one event given by the other event has occurred is equal to the joint probabilities of the two events divided by the probability of that given particular event. This is how we demarcate this PA given B, joint probability divided by the probability. Or on the flip side also you can define PB given A. This is the same. A intersection B or B intersection A. Now these ones, unions and intersections, students, you can write it in either way. P A union B. Even if you write it as P B union A, these are same. On the other hand, P A intersection B, B intersection A, however the way that you write it, these are same. Okay. So conditional probabilities, you can simply take the joint probabilities or the ands and divide it by the respective event that has already occurred. B has occurred, B. A has occurred, A. How do you keep this equation in mind? Easy. You take the probability that is on the bottom part, that is the area that is here. See, B given A goes to the bottom. A given B goes to the bottom. That's a very easy way to keep things in mind. Okay, got the broad idea. There's something called the conditional probability where you can discuss about two events, second event occurring provided the first event has occurred. That's the broad idea of conditional probability. Now coming to this next rule, that is on the independent events. Two events, A and B, are statistically independent if probability of one event is not impacted by the occurrence of the other event. So pretty much straightforward theory. Independentness means one event has absolutely no impact to the other event. One event, no impact to the other event. That means, in that case, you may not see some commonality between these two events. Why? They are independent. Something like this. A is sitting here, B is sitting here. No some sort of a dependency or no commonality. By using the Venn diagram, it's to define the independentness and the this mutual exclusiveness, but try to get a broad idea. Once is independence, these events, the probabilities has no impact to the occurrence of the other event. So in such cases, students, this P A intersection B is going to be null and void. P A given B, no dependency on B, so it is only left with A. Even P B given A, no dependency on A, so it is straightforwardly probability of B. So for an independent events, it's very convenient to identify if the joint probability is going to give you the same probability of the event that you're focusing on. That means such instances you can finalize this as independent events. So in such instances, students, you can multiply also. The multiplication rule can give you the independent events for the commonality. PA intersection B is going to be PA into PB. Yep. So that individual probabilities of PA, let's say something like probability of A is going to be something like 30%, probability of B 40%. So this is going to be 12% in that case. That's why I told you it's a bit difficult and it's a bit tricky to define the independentness using a Venn diagram. One could get a bit carried away with the idea of how do you calculate the multiplication provided that you don't have the commonality, but it's not the case. The broad idea is that statistical independence means the first event occurring will not have the impact for the second event. Okay, see, it's something like I'm taking the umbrella on my own, 50-50. Raining, 70-30. So if I call these two events as independent, umbrella event, rain event. If I demarcate, okay, that means irrespective of whether it's raining or not, some days I may take the umbrella, but some days I may not take the umbrella. I'm not really going to look at the sky and take a determination, no, but broadly depending on my appetite of taking the umbrella or not. If I'm taking a heavier bag, I may take the umbrella. Likewise, there are different other factors for this instance. So in such cases, these two events are can be named as independent events. Raining and taking the umbrella independent, but you can calculate the joint probability also. That means you can multiply. Taking the umbrella 50, raining 70. So the for a given day, I'm going to go with the umbrella on a rainy day is something like 35%. Likewise, you can calculate the multiplication rule in such instances. Okay, clear? Conditional probability and independent events. These are two very important rules to keep in mind. The last and the most important out of our today's discussion is the mutually exclusive events. Now, once you discuss these three only, you will get the total picture of these individual elements and their relationships. So bear with me till I give the explanation to the last one also. Then we'll try to rethink and rediscuss the uh, independent probabilities, conditional probabilities, and the mutually exclusive events. How do you define two events are mutually exclusive? Is by if there are no common elements in both events. If there are no common elements in both events. If there are no common elements. In other words, PA and B should be equal to 0. Actually, now that Venn diagram that I wrote previously is a bit more suitable for this instance to discuss. Now, I would say it's not very good explanation if I use it in the previous one, independence, but it has a similar meaning, but from area wise, it's very difficult to explain. But for the mutually exclusive events, you can easily discuss this with a Venn diagram. Why? Simply because of the fact that from area, you can identify this pay A and B should be equal to 0. There are no common area over here. No common area. In that case, what is going to happen? That means P now this doesn't say this mutually exclusive, doesn't really say whether there's an impact or otherwise. There's an impact or otherwise that we will be discussing the independent events scenario. So one could combine these things also, independent and mutually exclusive. Not mutually exclusive, not independent. Likewise, there are maybe 4 different instances that you can define for any event. But let's first try to learn by separation, then we can combine it anyway. So broadly, if events are mutually exclusive, without mutually exclusive students, we used to write something like this: PA union B is equal to PA plus PP minus PA intersection B. This is how we used to write. But now that what is going to happen? This part no longer there. So we are going to left with, in such instances, PA plus PP only. PA plus PP only. Yeah. If there are non-mutual exclusive cases, only our traditional and original arguments will be there. Why do we take out this A minus B once again? If I try to quickly recall, is try to double count this particular area. Yeah, A, B. This is the A union B. We take A, take A, B, and then we minus A intersection B once to avoid the double counting. Okay, fair enough. Now let's try to quickly recap these 3 events once again. Conditional probability. What do you mean by this? Is simply you are going to define the probability of one particular event given the other event has occurred. Now these two events will have some sort of a conditionality, commonality. Independent events, on the other hand, are the strange animal here. It is merely going to tell you the fact that one probability is not going to be impacted by the other probability. Something like there's a machine in a factory, there's uptime 98%, downtime 2%. There's another machine on the other department, uptime 90%, downtime 10%. 98 to, let me quickly do a sketch to clarify it a little further. Machine 1, uptime, downtime. Machine 2, uptime, downtime. This is 98% and 2% downtime. Second machine is a bit more troublesome one, 90 up, 10 down. Now this uptimes and downtime, students, now this probability of machine 1 up and machine 2 up. If I just name it as uptimes like this. Now classically, in that example, one could say, okay, fine, these machines are working independently in two different locations, not having one input to the second as the output. So effectively, this 98% and 90% are statistically independent. One machine, no physical relationship with the other machine, so effectively, no impact to the uptime. No impact to the uptime of the second machine. So what's the joint probability? So P A intersection B, in such instances, you can multiply these two events. 98 plus, multiplied by 90. And the common in that case, if one asks me, okay, what's the both machines being up and running 88.2% of the time. Machine 1 up and 2 down, you can multiply like this also. So the broad idea of this independent events is nothing but we're not going to be defining anything on the areas, not going to be defining anything on commonality. Rather, we are arguing on the fact that events are independent. So one probability, no impact to the second probability. Last one, mutual exclusiveness is where from area you can easily argue. What's the angle that you can argue is whether you can find anything common in the A intersection B or otherwise. A intersection B or otherwise. If there are commonality, of course, a diagram like this is going to occur, and non-mutually exclusive is the instance. If there are no commonality like this, no commonality, then we can call it as mutually exclusive events. Okay, that brings us to the past paper discussion part. Yep. Quickly, I think we have a bit more questions to be discussed today. I doubt whether we can find time, but let's try to, take you through a couple of questions and do the calculation. If you could bear with me for another 10-15 minutes, I think we can have an effective discussion today. First question I'm quoting from a bit more of a longer question paper. Sorry, older question paper. 2016 March, question number 1. Okay, we'll read the question together. In an employee survey of a bank, 45% of the employees are male and 70% are economic graduates. The probability that an employee chosen at random is either female or an economic graduate is. Now, one would say, okay, fine, we have learned in one particular angle of trying to resolve simple questions, but the examination questions are a bit more tough. One would argue like that, but then again, if you try to simplify the situation by using a Venn diagram or a tree diagram or any simple graphical representation, still you can come up with a number easily. Okay, don't worry. We try to resolve this. Okay, so now since this is a matter of gender, I can either use a Venn diagram or a tree diagram, simply because of the fact that my set can be defined nicely into two angles together. Yep. So let me try to use a tree diagram over here for a change. Fine. I start with an employee, 45% and 55% is my first division. What is this? 45% are going to be male. And if that is the case, other 55% are going to be female. And 70% are going to be economic graduates. 70% are going to be economic graduates. Fine. It's a bit of a tricky part now. Now, how do you demarcate it? If you take 70% over here, 70% over here, 30% over here. Is this going to give me an answer? Either female or economic graduate is going to be my question in focus. Okay. Now, the employee random either female or now this is the interesting part. Okay, if I am going to choose an employee for this particular computation as an AND, what do you mean by AND? Okay, now I have some set like this, and is going to be the combination. No, it's not the case that is being asked. O means I can find the probability of either female. That means what's the total number of female population? It's going to be 55. Isn't that so? 55. Yeah. Give me a second. Yeah. So this is 55. And on the other hand, now I can demarcate, okay, 70% are economic graduates. If that is the case, I can assume, fine, out of male 45 population, there is going to be a 70% of economic graduates. And if that is the case, 30% of non-economic graduates. So my question in focus is asking either I can find some female population like this. Now, am I bothered whether I'm going to get economic graduates or not? No, it's female, 55%. And on the other hand, there's another branch coming up from this particular area. Why is that? There is a probability of, from probability point of view, one can argue, okay, there's a 70% chance that out of the male population also, there are economic graduates and non-economic graduates. So effectively, students, if you do the computation, you're going to get an answer something like 55%, that is female, plus econ graduates of coming from male population. Out of the 45%, 75% population is going to come from the male economic graduates population. So this is going to be 0.55 plus, I have to multiply plus 45% by 70. It's going to be 0.315. If I add these two numbers together, I'm going to get a number close to 0.865. And the closest answer that I can see is 0.87, or answer number A. Answer number A. Good question, isn't that so? You can argue from different perspectives, and you may use something like a Venn diagram or a tree diagram. Even if you try to do a Venn diagram also, you may have to stick to the same assumption, isn't that so? So you will have something like male and female population being divided like this, female, and in the male population also, then there's going to be another deviation. This is economic graduates and non-economic graduates. In the female population also, something like this, economic graduates and non-economic graduates. But eventually, students, you cannot resolve this question by taking the assumption of whether this economics and non-economics is going to be 70% and 30%. Otherwise, there's no definite answer for this. Yeah. So that's how I told you. I mean, you can't define something like this traditional Venn diagram here. Yeah. So Venn diagram could be any diagram as long as you demarcate your areas correctly. Okay. Bit of a tough question to start our discussion, but don't worry, there are different styles of question. And probability questions, again, students, you have to be very careful. The breadth of testing a probability question is endless. If you take something like a last pairs or partial index in an index question, you may see always examiners trying to stick to one of these two methods and try to ask you to compute one of the indexing methods. But for a probability question, students, there are many hundreds and or different arguments that you can bring it in a question. So you have to be a bit creative and always assume whenever you're not sure. Yeah. The same question paper, question number 8. A and B are two events. PA is given, PP is also given. PA intersection B is also given. Calculate PA given B. Now this given mark is not clear in the question paper, but don't worry, we'll try to the theories that we know. PA is given, this is 3 divided by 7. Since there is an intersection, I have to draw it like this. A intersection is 1 divided by 9. PB, I know this is as 4 divided by 9. Yeah. So, what's the question it is being asked? Calculate the PA given B. We know in such instances, we can easily write PA intersection B divided by PB. What is in the bottom comes to the bottom. PA intersection B, 1 divided by 9. PB, 4 divided by 9. And the answer is going to be 1 over 4. Since it's a calculation, you need to, when answer has to be 1 over 4 or 25% or 0.25. Any of these answers is correct. Huh? Okay, great. 17 March question paper. I have question number 1. I quickly calculate the question paper. An apparent factory in B, has 10 production line. Now, this is a classic example that we discussed a moment ago, isn't that so? On past evidence, there is an independent probability. Now, we have to highlight this part. See, independent probability. What is being suggested by that is that these 10 machines are going to be independent. These 10 machines are going to be independent from one another. There is a 1% of breakdown on any production line each day. The probability that there will be no breakdown on a given day is 10 machines. If it is independent, now we know we can multiply PA and PB and calculate the joint probability. Calculate A and B up. If these are machines, then I'm going to define something like PA1 multiplied PA2 multiplied by PA3 up until PA10. Yeah. If I'm going to demarcate this AN as my uptime, that's this. This is going to be 99%. This is also going to be 99%. Similarly, up until the 10th machine, it's going to be 99%. So, what's the answer? since it is independent events, the joint probability, the question is asking the probability that there will be no breakdowns on a given day. See, that's why I straightforwardly try to get this 99% into the head. No breakdowns as in, there is a 99% chance the machine is up. If there is breakdown as in, there is a 1% chance the machine is down. Yep. 99, 99, 10 times. The answer is going to be 99 to the power 10. Answer is going to be D. Yeah. Independent events, independent machines, independent probabilities, so you can multiply. Okay. 17 marks, same question paper. Question number 6. Question number 6. Now this question, of course, let me quickly see. Now this question effectively have 4 different parts. Now this part number 3 is having 5 marks. From traditionally, there's this one question in this particular exam paper, which has something like this 4 subparts, each having 5 marks. So it's a bit of a lengthy question to answer, but the questions are put it in a way to not to test some advanced theoretical areas, but to test maybe some fundamental theory. So this is one such thing. Okay, part number 3. We'll quickly read it together. The probability of a company obtaining contract X is 0.3. Contract Y is 0.5 and the contract Z is 0.6. There are 3 contracts. X, I'm going to just write Px is going to be obtaining X. I have to define it, but in the interest of time, I'm quickly writing without writing my assumption. Now, if I say this, I have to write it perfectly. Probability of getting X, getting contract X successfully is what I meant by Px. Yeah? Compute the following probabilities. Probability that the company will obtain only contract X and contract Y. Now, once you see these numbers, students, what do you mean? What can you assume? You can easily assume that these are going to be independent ones, isn't that so? Has they mentioned anything about if you get X, you will not get Y? There is some sort of a dependence between one company getting multiple contracts. No, nothing is like that. So easily you can assume that these are going to be independent contracts. So in that case, students, you can easily multiply these events and calculate the probability. See, only contract X and contract Y. That means you're getting X. Px is fine, Py is fine, and 1 minus Pz has to be the case. Px is 0.3, Py is 0.5, and this one, it's not 6%, sorry, it's not 60%, it has to be 40%, right? Is a fact that question is asking only contract X and contract Y. Only contract X and contract Y. So if you do the multiplication, you have to get an answer close to 6%. 6% or 0.06. Second part, probability that the company will obtain at least contract X and contract Y. Look at the wording carefully. At least contract X and contract Y. So in that case, probability of X is fine. Probability of Y is fine. And once you see the word at least, what can you think about probability of Z? I'm okay. Even if I get it, also I'm okay. Even if I don't get it, I'm okay. So that means this part about probability of Z, this is implied as 1. Why? I'm getting at 60%, not getting at 40%. So the word at least is going to suggest you, I'm not going to really care about the contract Z, isn't it? So I don't mind. I will only look at the probability of X and probability of Y getting into my hands. 0.3 into 0.5 is going to be 15%. See, that's how you argue in this particular question. The English, the The way the question is being put it in is the most important thing, not the probability number, students. See, I mean, the theoretical point of view, you can argue from different angles, but I urge again and again, try to get the wording clearly to your heads, and then only you can argue. Yep. Quickly, there are only two more questions to be discussed. I hope you can bear with me. We will try to discuss and finish it off so that freshly we can start the discussion on the next week. Question number 9 of the 2019 March question paper. Let me read the question. A factory produces 80% of the items in line A and rest of the items in line B. In line A, 5% of the production is faulty, whereas in line B, faulty proportion is 10%. Calculate the percentage of probability. Calculate the percentage of faulty items in the total production. Now, since I did a tree diagram, this time let me try to do some sort of a Venn diagram. Now, I can assume, okay, since 80% of the items are coming in line A and the rest in line B, I can do my demarcation like this. See, 80% of the items coming in A and 20% B. And if I do something like this and call it as the faulties, it's fine, right? So all these are the good items. The one in the ellipse or the circle are the faulty items. In line A, 5% of the items are faulty, and whereas in line B, faulty proportion is 10%. Now this is where I have to be a bit careful. If I write 5%, no, it's not going to be the good representation. Why? This 5 is going to be out of the whatever the coming in this particular area. Okay, so let me just keep it in mind and try to keep the numbers in straight. What is being asked here? Calculate the percentage of faulty items in the total production. If I write it something like this, using a bit more mathematics, something like probability of faulty items. Probability of faulties are going to be coming from probability of faulty given A, probability A, plus probability of faulty given B, probability of B. What could you think? What I have done here. Now, the conditionality, I have put it quickly into an equation. Faulty given A is the area, this, multiplied by probability. That's why I told you the first 5% I can't really take it. Why? If I take it as 5%, this is going to demarcate, no, from the entire production, 5% is faulty. If I take this as 10%, so this has to be 10. Is that the case? No. That's how that's not how the question is being put it in, but rather the faulties are given so that the conditionality could be applied here. Conditionality could be applied here. So eventually what I'm writing here is probability of faulty, and I'm bringing in two areas together. This area plus this area. Yeah. So I can fill up the gaps. Probability of faulty given A is nothing but 0.05 multiplied by probability. Now this is logical. Why? Out of 80%, 5% is faulty. Even if I take the probability of now this one, 0.1 is the faulty percentage out of 20%. Yeah, out of 20%. Now it makes sense, isn't that so? So out of 20%, 5% are faulty. Out of this 20%, 10% are faulty. If that is the case, now these are going to be the faulty numbers. If we add it up, 0.8 multiplied by 0.05, I'm going to get 4% over here, plus 0.1 multiplied by 0.2, I'm going to get 2% over here, and 6% is my faulty percentage. It's the complicated way of resolving this question. Rather, if you simply do the multiplication like out of 80, 5 are faulty, plus out of 20, 10 are faulty. If you do this addition, you're going to get the same number. But effectively, I just want to, draw up a Venn diagram, show you that things could be argued from different angles, and show you the application of the conditionality also. Yep. This is 19 March, question number 9. Last question for the day. Last question for the day. A 19 September paper. Now, although this is mentioned as part number 2, this is not the, again, it's not a compulsory question. It is coming from question number 6, that is a bigger question, part number 2. So this carries also 5 marks. 5 marks. Chinese company bids for the construction of 3 sectors, A, B, and C of the Central Expressway. The probability of this company obtaining sector A. Let me quickly write this like the previous example, 0.3, B as 0.5, and C as 0.6. Compute the following probabilities. Probability that the company will obtain only sector A and sector B. Only sector A and sector B. If that is the case, we should not get sector C. Yeah. PA, PB, how you put it as 1 minus PC. Clear? 0.3, 0.5, and 0.4. 0.4. 0.3 multiplied by 0.5 multiplied by 0.4 is going to give you a probability of 6%. 6%. Second part, probability that the company will obtain at least, look at the wording carefully, is only at least sector A and sector B. If that is the case, we're talking about PA, PB. What about PC? We don't care. Why? At least sector A and sector B. About sector C, we don't really care. It's 1. 0.3, 0.5. This is 15%. So this is a question. It's been repeated by 2 instances in 16 March and 19 September. So you can easily get carried away by the English. So be careful on how do you put the probability-based questions. So thank you for the little extra time. I can comfortably come to part 2, and we are discussing the continuation of few more rules and going into normal distribution, and we are learning how to apply the standard normal distribution throughout the rest of the day. So I can be at your disposal for another couple of minutes if at all you have any questions on the today's lesson or the questions that we discussed so far. And on the on what Mr. Kavindra of the IBSL mentioned on the extra classes, I believe the population who attended to the classes must be either working from home or mostly going to work. So if that is the case, I think if I arrange a class somewhere around maybe 5 to 7 or 5:30 to 7:30, still you will be bit at an uncomfortable position to attend to the class. Is your other classes mostly having 7 to 9 in the afternoons? I believe 7 p.m. to 9 p.m. If that is the case, and if you don't mind, may I discuss with Mr. Kamindra and try to organize maybe one class in the afternoon where your other classes are not going to clash? I think I saw that Mr. Kamindra also mentioned, and Ms. Imadi has also mentioned the fact that you're having another class on Wednesday. So if that is the case, either Tuesday or a Thursday, or maybe even a Friday, let me try to put up another class, and maybe prior to a couple of days before, I will try to schedule it, and also to inform it you bit advance. so that you can be prepared. Don't worry, we are just continuing our lesson what we learned today, that is on the probability and the standard normal distribution. Are you okay with the timing, the date? Let me kindly confirm with you after the discussion of the IPS and stuff. I have to check whether there are any other subjects being clashing. Is the timing fine with you guys? 7 p.m. to 9 p.m. in that case? I will, with the silence, then I will assume that it's okay. So the timing I
Yes, sir.
have, great, great. So the timing I have taken with the assumption that you will need time to go back to home and be a little bit ready for the classes. Otherwise, I don't think it's a prudent idea to, try to have another class in the weekends, because I'm sure that your schedules are packed with the other elective subjects and the compulsory subjects. So bear with me. Maybe a Tuesday or a Thursday or a Friday, depending on your other classes are not getting clash. Let me quickly schedule a class and inform you well in advance. All right, ladies and gentlemen. Then, if that is the case, I can leave with you, so that I've shared my email with you. If at all you have any questions, just shoot me an email, or we can discuss anything on the next class. All right, then I'm signing off. Thank you.